If we are to accept that nature has to be fundamentally described through probabilities, we have to confront the fact that all the physics prior to Maxwell and Boltzmann was based on deterministic laws. How can these conflicting views be reconciled? The answer stems from a fundamental mathematical result in probability theory known as the central limit theorem. The theorem shows that some quantities, which are the result of combining a very large number of random quantities, have very little uncertainty in them. The uncertainty kind of averages out, and we can show this very precisely. I think it's worth to explore this a bit more closely, for it actually holds in it the key to understand the connection between the chaotic microscopic world that Boltzmann hypothesized and the orderly macroscopic world we've always known. This connection is the key to statistical physics. Quantum mechanics has actually made the connection much more subtle, but that's for another time. As a way of seeing the central limit theorem in action, I'm going to use MATLAB to show what happens when you add together more and more random quantities. Rand n, 1, n creates n normally distributed random numbers. Cum sum adds them one by one, putting the results in a new array, which we can plot in blue. What we plot on the x-axis is the number of random quantities we have summed, and on the y-axis the result of the sum. By the way, this is also known as a random walk in one dimension, the y-axis, where the x-axis is like time. We can repeat this random process 100 times, plotting them in the same graph. Our position in the y-axis, after n steps, is the sum of the n random variables, and so this width should be like the standard deviation of the sum. As we increase n, we can see that the paths are looking more and more like a simple straight line. This is because the standard deviation after n steps grows like square root of n, while the number of steps grows like n. So the ratio decreases with n as 1 over the square root of n. We are interested in the ratio with respect to n because macroscopic quantities are often proportional to n, so that this result means that our uncertainty in these quantities will decrease relative to these quantities as we increase the size of the system, like the number of particles. A way of looking at this is that the randomness is less and less apparent as the randomness happens at smaller and smaller scales. If it happens at the scale of atoms, the randomness is almost unnoticeable at the scale of apples and oranges, unless the randomness also manages to add up to microscopic sizes by some nonlinear effect, which happens rarely, but it's one of the ways interesting things can happen. An example is what's called critical phenomena, which occurs, for instance, when you boil water at a very particular temperature and pressure. So we can actually show that the standard deviation of the sum of random quantities grows like the square root of n. We'll do the calculation using the energy as an example. The definition of the standard deviation sigma is as follows, where sigma square is the variance in probability theory. Angle brackets here represent expectation with respect to the probability distribution over the velocities of the particles in the gas. We can use the famous binomial result to rewrite the squared expression. Using linearity of expectation, we can push the angle brackets over the sum as follows. Noting that the expected value of E is a constant with respect to the distribution of velocities, we can remove the redundant angle brackets, and we can merge these two factors together. These two terms can be summed together, giving minus expected value of E squared. Now, let us finally write the expression for E, which is the total energy of a gas of particles. Because this is an ideal gas, there's no interactions, and all the energy comes from the kinetic energy of each of the particles. So E is the sum over all the particles of the kinetic energy of each particle, which from basic mechanics is m times the velocity v sub I of that particle squared divided by 2. We can substitute that expression for E in our expression for the variance, sigma square. Now, we have a squared sum here, which can be split as a product of two sums which have a different dummy index, I and j. Again, using the linearity of expectation, which is the angle bracket, we can take the sums out. Let me just add some parentheses around this that will make things clearer. And use again the linearity of expectation to take the sum out of the angle brackets, but not outside of the parentheses. Now, this double sum is the sum over all pairs of I and j. We can rewrite it as the sum over all pairs I and j which are equal, plus the sum over all pairs I and j which are different. And the overall sums will still be the same. So let me clearly split those two sums up. Now, because I and j are the same in this term, I can substitute I into j and merge these two factors together. Now, because we assume all particles are identical, every term in this sum is exactly the same, and so we can substitute the sum with just the total number of terms, which is capital N, the number of particles. Plus we don't need the index I anymore. Now let's go to the other term. First of all, the velocities of two different particles are assumed to be independent of each other in an ideal gas. Therefore, using the basic rule of probability theory, the expectation of the product equals the product of expectations. Now, just like all particles are identical, all pairs of particles are identical. Therefore, all terms in the sum are the same, and we can substitute the sum with the number of terms in the sum. Now, the number of distinct pairs is n, the number of possible choices for the first particle in the pair, times n minus 1, the number of possible choices for the second particle in the pair. And again, we don't need the indices anymore, and we can merge these two factors together. We can apply the same argument of identical particles to the final term in the expression. And let me distribute in the power over the factors in the parentheses, as well as expand out the second term as follows. Let me just move this term to the left so that it's a bit more clear what I want to do. And here I can see that I made a mistake. So if you were paying attention, you should have spotted this out. This second term in our expression comes from this term in our previous expression, which, if you were paying attention, actually had a negative sign when we derived it, and I just miscopied it. So this will have a negative sign, which will give a negative sign over here, which means that I can cancel this out, as they should do. Now, using linearity of expectation again, I can take out the constants from within the angle brackets, as well as tidy them up a little bit. Let me distribute this power in, simplify it at 2 squared on the bottom, so we can see that we have these two factors which we can collect out of the two terms. We can see that the variance, sigma squared, is proportional to n. That means that sigma, the standard deviation, is, if we take the power to the other side, proportional to the square root of n, as we can see here. We can even find from this calculation the proportionality constant of this relation. Note also that the expected value of the energy grows like n, so we can see that, as we wanted to show, the uncertainty in the energy appears smaller and smaller relative to its expected value as we increase n. By the way, because all of this means that the deterministic description of thermodynamics will be appropriate in this limit of n going to infinity, this limit is also called the thermodynamic limit. Now, the key here is that the macroscopic value of energy seems to have a determined value, even though we know that microscopically each of the particles' energy is random. Of course, what happened historically is that people observed that macroscopic bodies have a certain value of energy which doesn't appear to vary, at least up to what they could measure, their precision. And so they just assumed that that was a fundamental property and called it temperature. Similar quantities can also be derived by sums or combinations of very, very many microscopic quantities in such a way that the central theorem applies, and so these microscopic quantities have very little uncertainty in them. Things like pressure, volume, energy, magnetization, your size, your velocity, your rotational velocity, all these quantities which we use in macroscopic physics turn out to be quantities of this type. If one is able to show that these almost certain microscopic quantities have relations between them, then we will have what we wanted, deterministic laws from this random microscopic behavior. All we need to ignore is the completely negligible uncertainty in this microscopic quantity. This is what will give the deterministic ideal gas law. This is also the modern way of understanding the derivation of the laws of thermodynamics, fluid dynamics, elasticity, etc. Of course, from this deeper understanding of the classical laws come two extremely important advantages. One, we can compute all the constants that depend on the material at hand, things like the thermal and electrical conductivity, the elastic and friction coefficients, viscosity, etc. We can just derive them from the knowledge of the atomic composition of the material and the probabilistic behavior of these atoms. This is in general quite hard, but can be approximately done. Two, we can also gain insight into an incredible wealth of phenomena that follows outside the classical laws. During the last century, we have discovered that there is just so much phenomena for which the conditions for the central limit theorem or other of the assumptions of the classical work simply don't hold. However, statistical mechanics can still be applied microscopically and can often give insights into the complex macroscopic behavior. This includes things like non-Newtonian physics, polymers, phase transitions, critical phenomena, biophysics, etc., which I will hopefully discuss in future videos.